basic things you remember, right? What usually we do and how we need statistics, where exactly statistics is helping me to understood that, right? So statistics is the concept and Python is the programming language that is enabling me to write down the codes to do the operation in Python, using a computer. So just understand this thing. Statistics is all about theory and Python is helping me to put that theory into picture to solve that theoretical stuff. How, like, finding correlation is a statistical concept, but Python's, this dot core is a function which is enabling me to do particular that operation. So that is the difference. Now, uh, there are few things we have seen here, like, how to select a data from a larger data set, which is population. From that, we will take a small data, which is sample. And then based on that sample, we will do our selection, our whatever operation. And if we are okay with the result, then we will apply that to the larger population. That is what, in general, how any operation works. Now, for any traditional machine learning thing, this technique is a little different. This technique is a little different. Different as in, okay, multi-collinear. Let me just finish this one. It's the last one. So we saw these are correlations, right? These all are correlations. So sales and profit. So to go to matrix, which will show how sales is impacting profit or how profit is impacting sales, vice versa. Both is true. Like if sales has a 58% correlation with profit, you can also do the same thing. Like profit has a 58% correlation with sales. Both are the same meaning. And the better the correlation it is, that means the better one variable can impact the other variable. So that is the case with two variables. Now, multi-collinearity will come here, but before that, I have to explain what a linear regression is. So until now, did you get an idea of what a linear regression could be? So what is regression, right? So you remember I only talked about classification and regression. Can you recall it? One, okay, let me just rephrase that. Types of ML problems. There are two. One is classification and another one is regression. REGRESSION. So there are two types of machine learning problems. One is classification and one is regression. Now what are they? So classification means, as the name says, if you want to classify the final outcome, that will be a classification problem. And a regression means if you want to forecast the final problem. So if I see the literal meaning of regression, a regression is a return to the previous or less advanced or worse state or way of behaving, right? So regression is a return to a previous or less advanced, means either backward or forward state. So that means if there are some values, then how much one value is impacting the other. So kind of the mix of a bit of correlation that we have already seen. So that is it. So or we take any other example. So the same ones here. This we have already seen this hard sample data set. So we have all of this data, right? We have this data with us. Now, based on all this, I have to predict what will be the value of this. Let's say I have only this many number of records. Let's assume that this is what a client has given me, only the yellow colored close. And the client wants me to create something out of it so that I can predict the future value. How essentially this works. So this essentially goes like, so this is my input data. Based on this input data, I will create a model. Based on this input data, I will create a model. So this will be my model, right? So what model? So model means something or a function or something which will have these as the input, and for this input the model knows these are the outputs. So if the model can identify this, then in near future if I give this as output, the model will give me something as the output. Now then I have to check whether the model's output and the real output are matching or not. If we are close, then the model has really worked. If we are different, then the model has failed to work, right? So let's take a simple example. Let's say Indian 11 players are playing for Indian cricket team. Based on first 5 matches, can I take a call that who should bowl first, who should bat first, who should bat in second term? Can I take these calls?
Duplicate that table now.
So you said, let's say they are, India's, let's say IPL, CSK is playing a match, right? So in that IPL, based on first 5 matches, can I say which player can bat first and which player can bat second? Can I take these calls? I can, right?
Yes, yes, we can.
To some extent, we can take that.
Hmm.
Let's say their IPL, CSK has played 5 matches or 10 matches. So based on those 10 matches, I can see which player is constantly performing at the initial overs, which player is constantly bowling for the slog overs, and all those details. We can do that. So if we put all those informations together, we will call in statistical terms, we will call it as a model, because the model knows which player bats at what time and can perform better. Which bowler, if bowled at a certain time or at a certain over, will do the best of the bowling. So that information is stored together inside the model. Now, if we predict something new, if we want to predict something new out of it, what we will do, we simply have to give the new players, let's say there's a new player that CSK has bought in. I just have to give the existing, the new players details, like how much run he scored, at what time he got out, what time, how long has he played, and all of those details. And the model can tell me, okay, this player looks more of like a bowler, so make sure he bats after 6 down and he bowls in the second over or something like that. So that is the prediction. That is the classification that I'm doing. That is a model. That is the model we are talking about. So model is something which has all those informations. How I will just share that piece of information with you. How model does all of that. So essentially the thing is, if we are classifying between the final variable, which is discrete in nature, discrete means things which are either or, like this is the final value. The final value it has only two values, right? Either 0 or 1. So this is a discrete value, so there is nothing in between, like 1.257, there's nothing like that. There is no value which is 0.112. No, it's either 0 or 1, like a switch. Either the fan is off or the fan is on, like that. So if we have to deal with those kind of situations, that will go under classification problem. So you are classifying whether it will go to class A or class B, class 0 or class 1. That is a classification problem, right?
Okay.
And if we are talking about numbers, like the next value could be anything, there is no limit. That is just remember the main thing. For classification problems, we have a limit that the value will lie between this. It cannot be your output has to be 0 or 1. You cannot have an output of 3, 5, 10 or something. No, it has to be the 0 or 1. That is a classification example. Regression, on the other hand, the value could be anything. any finite, infinite, not infinite, any finite numbers from minus finite to positive. Like, anything on minus, anything positive, any decimal, anything, any numerical format. So that is known as the regression problem. Is that clear?
Hmm.
Any doubts, Ranjit? Just let me know.
No, no.
So tomorrow, if you want to, if you go to DMart and you want to buy some, potato, let's say how much potato will you buy? So what kind of problem is this? Is it a classification and regression problem?
Potato means recreation.
Huh?
Recreation.
Regression. Why regression?
It is not a value, potato.
Yes. So the question says how much. So it could be anything. It could be 1 kilo, 2 kilo, 10 kilo, 100 kilo, anything. So that is a regression problem. You are predicting a number which could be anything. There's no limit to that number. But if I ask you the question, like, are you, going to buy India Gate rice or let's say another company rice? Right.
It's
If I ask
classification.
you these type of questions, or let's say if I ask you to, what are you going to buy? Are you going to buying, potato or onion? So the final outcome is fixed, right? The final outcome is fixed. You are going to buy either potato or onion. That is a classification problem. Getting confused or
No, no, no. No problem.
okay, all right. So that is the main thing. So the thing is, so that is the classification and regression. Now, classification we will come later. For now, start with the regression problem. The regression problem. Let's start with that. So, for regression, there are essentially two types. One is simple linear regression, and the second one is multiple linear regression. So, there are two types of regression problems that we have, right? One is simple linear regression and one is multiple linear regression. Why is that? What is that? So single linear regression means your equation will be like this. Y is equal to beta 0 plus beta 1 into x. So that will be your simple linear regression. That means x is only 1. But if you have more than this x value, beta 1 x1 plus beta 2 x2 plus let's say multiple other values plus beta n xn. So understand what is happening here. So okay, first before that, just understand what do we call them. So there are two types of things. Just 1 second, give me a moment. Yes. Oh. Hello?
Yeah.
Yeah. So there are two types of variables that we have in a traditional machine learning problem. One is independent and one is dependent. Now, you can see easily which is what. So let me just open that same database, that same one. So this is the one we were talking about, right? The same data set, some predicting some value. So let's say we want to predict the heart column, heart disease 0, 1 based on these variables. Or okay, let's keep it more easy. Weight and height, let's say 135 centimeter to 195 centimeter, random between 45. Let's say this is something which is happening. So this is the data that I have. One is height, one is weight. Height is in centimeter and weight is in kg, let's say. So my question is, I have given this data set. I was given this data set and I was asked, can you tell me what is the relation between these two? And if I have some new heights, would I be able to predict the weight? So let's say that is the question. So I have been told like weight is the variable that I want to predict. I have to predict which one? I have to predict the weight. This is a variable that I want to predict. Right? And based on what? Based on height. So here what usually we do is, now first thing is, this is a regression problem because the outcome variable has multiple values into it. It's not limited to 1, 2, 3 or something like that. It's n. It's a regression problem. So that is the first thing. Now, what type of regression? So regression we understood. It's a regression problem. It's not a classification problem. Now, what type of regression? Is it a simple or linear? So for that, we will see about dependent and independent first. So what is a dependent variable? So a dependent variable is something which depends on other variables to get the value. Like here, I have to predict weight. So the weight value depends on height. Weight is a variable whose value depends on height. So my dependent variable here will be weight. And my independent variable will be height. Just tell me if you are able to understand this part or not.
Okay.
The thing which you want to predict will be your dependent variable. So dependent variable will always be one because at a particular point, you cannot predict multiple columns. You have to, in a machine learning, you have to predict only one variable at a time. So your dependent variable will be only one that depends on something else. But on the other hand, the height is something which has a can change any, which does not depend on anything, which changes on its own. So those variables are known as independent variables. Those variables are known as independent variables. So this is your predictor weight. So the variable that you want to predict, that is your dependent. Other than that, rest is independent. Now, interesting thing here is your independent variable could be one or more than one. The independent variable, there could be one or more than one. Now, coming back here, so if you have only one independent variable x, then that is a simple linear regression. So here, what is what? So y is my dependent variable. Y is the weight. Y is the this thing. Y is the weight. So this is my y. So y is equal to this one. This is my y. And height is my x. Right? This is my x. Now, if I have to derive a method, a regression method, then I have to create an equation first. What is the equation? The equation is like, this is the equation that I have to create. Y is equal to beta naught plus beta 1 into x. So that will be my equation. Beta naught plus beta 1 into x. So y we know is the dependent variable. X is the independent variable, which is height. So what these two are? Beta naught and beta 2. These are known as slope and intercept. Beta naught is known as the intercept and beta 1 is known as the slope. So what they are essentially? Now for that, I don't have anything to show here. So I have to take a small example. Linear regression. So a linear regression. So what essentially we are trying to do here. So if I just put these two and try to put it into a graph, this is how the graph will look like. This is how the graph will look like, because of course the values are like that. These all are random values and all are not in a good format or something like that. Yeah, even if I change, nothing will happen. So these all are random error values. But understand the basic thing here. Each point is a combination of a height and a weight. Are you following me? So let's say the first point, if this is my x-axis, the height is my x-axis, and the weight is my y-axis. So the first point is 135 into x-axis and 974 into y-axis. Probably that is my first point. 135, 74. So it will be somewhere around, no, 74, right? Yeah, 135, 74. That is first point. So if I put all those plots together, this is how it is going to take a shape. Now, this shape is very bad. It's not really a good shape. I make them little better. Let's say these are the values. So based on your height and weight, if I put them into a graph, this is how the graph looks like. Now, from correlation, what we have seen, the more the lines will appear in a linear line, that means more they have correlation amongst them, the more correlated they are. Or that is one thing from visual. And also we can check it from our functions in Python or Excel or whatever. So if I see, yes, they have a strong correlation, 96 percentage. That means for 96 out of 100, for 96 times, the height variable is getting influenced by weight or vice versa. Because to find correlation, it's not an independent or dependent. It's like just between two variables, how these two are close. Like if these are two friends, how much friendship they have. More the friendship, that means more they will try to help each other. Less friendship, they will not try to help each other. Just think it from that perspective. So 96% is the correlation between them. Very good. Now move on to the next line, which is how can we do something out of it so that if I put some heights here, I should be able to get the weights. So what I have to do, I have to come up with a mathematical equation. Which equation? This one, the one that we have seen here. This particular equation. That is something that we have to come up with. This equation can help me to predict something out of it. You following me?
Yeah.
Now, what is slope intercept? So we understood there is a height, which is my x-axis in this side. That means something which is independent. But the y is something that is dependent. For our case, the weight is dependent. So the weight variable is something that we have chosen that is dependent. So based on height, I want to predict weight. So X, Y sorted. So B0 and B1, what they are? So B0, like now, if I put a straight line here, how can I put it in Excel? This is the formula. I can put a straight line out of it. So this is the straight line that I'm getting here. Did not show me the. So I have something here. Okay, what these are, I'll come straight by one. So we can see here what Excel has done. Excel has tried to put a line so that this line more or less passes through all the data points. Now, if you're talking about line, then it's not possible that one line to go through all the points, right? Then it will not be a line, it will be a curve, right? But if we are talking about one line, then this is probably Excel finds it's at the best line. So if I, you know, if I bring the line towards the y-axis, probably between 40 to 50, somewhere it will have a cut, right? So if I bring that line towards the y-axis, it will have a cut between 40 and 50. So it will have a cut between 40 and 50. So the distance from 0 to that particular point where it will have a cut, that is your intercept. So that will be your intercept, right? And the angle this line creates with the x-axis, that will be your slope. Just tell me if you understood that point or not.
X-axis angle, huh?
X. So this is a line. Now these are the points. So the angle. So in mathematics, there is this angles, right? So the
138, 138 and 1.
if this it will have a cut at this line. So from that particular line, how much it is off from X? So it directly does not start at 0. It starts at probably 45 or something.
Hmm.
That will be your intercept. That means beta naught. That will be the value of beta naught, which is intercept. How much it is, how much is the distance from the x-axis origin? 0 point 45 or something. And how much angle it creates with the x-axis. That is something you have to just put it in the plot, and the angle is known as slope, which is beta 1. The angle that it creates, that is beta 1. That is about this particular line. That is about this particular line. That is about slope beta 1 and beta 0. So beta naught is the distance it has with the x-axis from the 0 point, and beta 1 is how much is the angle between y-axis. Now just ignore these angles and all of that. Come back to the basic, just ignore this. So these are mathematical terms to help you understand how the backend architecture works. Now let's come back to the actual equation. So this is my equation, right? Y naught is equal to beta naught plus beta 1 into x. So x is height and weight is the y, of course, the one value that I want to predict. Now, if I put this randomly on the graph, this is what the Excel is giving me, that hey, this is the mathematical equation between them. So this is the equation of a line. This is the equation of a line. So in mathematics, for any linear line, this is the equation. Any line, this is the equation of a line. Or in mathematics, they write it using y equal to mx plus c. Mx plus c. So same thing, m is the slope, the angle, and c is the intercept. In statistics, this has gotten replaced by beta naught and beta 1. So the thing here is, so what if beta naught is equal to 0? In that case, y is equal to beta 1 into x, right? If beta naught is equal to 0. So beta naught is equal to 0 means the line goes from this point, from the x-axis, from directly at the origin point. Right?
Hmm.
That is what beta naught 0 means. So beta naught is equal to 10 means the line will start from 10. Beta naught is equal to 50 means the line will start from 50. So that is what the beta naught is all about, the intercept. And what is B1? B1 is, I told you about the slope and all, but essentially this is the, we call beta 1 as the coefficient, is equal to, we call beta 1 as the coefficient. That means how much percentage of change we need to bring into x so that we can get the value of y. As simple as that. So let me just put it here. So this is simple linear. This is the basic equation. Y is equal to this. Now what they are, beta naught is equal to intercept and beta 1 is equal to slope, or we call it coefficient. We call it coefficient. So what is coefficient? Let me give you an example. What is coefficient? So coefficient, we can say it like as the importance of okay, let's say you want to travel through flight from, let's say, Chennai to some other place, right? Chennai to, let's say, Bangalore, or Chennai to Hyderabad. Now you will see the basic fare of flight fare of Bangalore or Hyderabad will be at a certain cap. It will not be below that, right?
Hmm.
The minimum will either be 4,000 or something for Bangalore, and for Hyderabad, the minimum will be around 3,000 or something. You will never see a price below that, and then it can go up based on demand. So that is your coefficient. That is the importance of that particular variable. Like if you want to go to Bangalore, minimum you have to pay is 4,000 rupees or something. Now then, number of factors. Number one, what is the importance? What is the time? Is it a direct flight? And you have taken food, and all of those points will keep on adding your flight fare. So you might end up paying 10,000 or something. So that 4,000 is, you just take the flight. You don't take any other options, no food, nothing, extra leg space, nothing. Just in flight from Chennai to Bangalore, minimum you have to pay 4,000 rupees. So that will be your coefficient, right? So that will be your coefficient, like that much has to be there. That is the connection between Chennai and Bangalore. You're getting my point,
Hmm.
or it's not clear?
A bit confused.
Okay, big time confused. That's absolutely not. So let me think of something like. So what is coefficient? Coefficient is how much percentage we have to. Okay. Let's say there are two bikes. One is a normal Pulsar and one is a some BMW, some hi-fi bike, right? Let's say you have two bikes. If you
Okay.
start these two bikes, can you say these two will go in the same speed and same everything will remain same?
No.
Of course not. So if you do a mathematical equation, if you just observe these two results, you might see that BMW speed is 1.5 times of Pulsar's speed, right?
Hmm. Yeah.
Let's say you rode the bike from Chennai to Salem or some other place and on probably on the beach, Chennai Marine Beach or some other beach. So you will have these observations that, okay, if I go with the same bike for 10 kilometers straight, uh, the speed I'm getting with the BMW bike is always at 150 or 180 kilometer, but the Pulsar is barely crossing 80 kilometer or 90 kilometer, 90 per hour. So you will see these two are connected through a common factor, which is how much times the speed differs. And you will come to this conclusion that, okay, the BMW bike is 1.5 times of Pulsar speed, right? You followed that, right?
Yeah. Yes.
So the BMW's speed is 1.5 into Pulsar speed. Whatever Pulsar is giving, BMW is giving 1.5 times of that. So what is this 1.5? 1.5 is the coefficient. It's the connecting factor between these two data elements. If these are two different variables, BMW is one variable, Pulsar is one variable, then 1.5 is the connection between them. Right? So if let's say I have these two values here, and let's say this has all speed here. So if the this speed is this much, and let's start with only these basic ones. Based on this, I came up to this equation. So this is what I have deduced, and also I have collected some data, and the data also talks about the same thing. Like the BMW speed is 1.5 times of Pulsar speed. That is the thing. So here, what is the coefficient? My coefficient, this thing is 1.5. That means I have to, if I have to get BMW's value, I have to multiply Pulsar's value by 1 point. Now, if I have to come back to the same linear equation here, so I need these two, beta naught and beta 1. So beta naught is the intercept. Intercept value I don't have. Intercept means how much time it takes to have a start from 0 to 100 or something like that. I don't have that information. So B0 becomes 0, beta naught becomes 0. However, what is the value of beta 1? This is coming 1.5. This is coming 1.5. So can I deduce a linear regression equation here? Yes. Now let's say if I select this as my y variable and this as my x variable. Why? Because BMW's value depends on the Pulsar's value. So I can take this call, or I can take the other one also. How? I can clearly say it like this: Pulsar speed is equal to BMW speed divided by 1.5. This is also true, right? This is also true. So right now, don't get confused, just think one at a time. So if this is the case, then I can straight away deduce the linear regression equation. So y, which is BMW, is equal to beta naught I don't have, which is 0. So let's ignore it. Beta 1 is equal to 1.5 into x. What is x? X is equal to my pulsar's value. So this is a linear regression equation. This is a linear regression equation. So tomorrow, if I have a new value, if I have, have a new value of pulsar, tomorrow, if I have a new value of pulsar, let's say at 90 kilometers, then using the same formula, I can deduce what will be the value of BMW. So just remember what I used. I said what will be. So I am predicting. So this is my existing data. Based on that, I deduced there is a relation between them, and what is the relation, what is the coefficient, that means what is the importance of pulsar with respect to BMW. This is the importance of pulsar. So once I have that equation in place. Next, for any value, I can deduce anything. Let's say tomorrow, if the speed of pulsar is 190, the speed of BMW will be 285. Ranjit, so you following now?
Yes.
What is the confusion now?
Nothing. Now it's understood.
Understood, right?
Yeah.
So, okay, just think one more important point here. So we saw BMW is equal to 1.5 of Pulsar. Why did not we choose the other way? We could have selected this one as well, right? Pulsar is equal to BMW divided by, so how much? 1 divided by 1.5. How much is the actual value? Okay, 0.6. So Pulsar is equal to 0.66 into BMW. So why we did not consider this equation and we considered this equation? Just can you think of? So the simple thing is the importance. So the more the value of coefficient, we will take that particular variable as our independent variable. Now here, this is one case. Here, Pulsar is the independent, BMW is the dependent variable. But for this particular case, this is also true. But here, BMW becomes the independent variable and Pulsar became the dependent variable. So why did not we choose this equation instead of this one? Because of the value of the coefficient. That means 1.5 is more than 0.6, which means Pulsar has a greater role to play to calculate the value of BMW rather than BMW to play the role of, to calculate the same for Pulsar because of the coefficient value, right? So that is one simple mathematics, just remember. So the more the value of coefficient, we will take that variable, as simple as that. So here 1.5 is more than 0.6, so we considered BMW as the dependent because BMW's value depend on pulsars and pulsar is an independent variable. There could be any value of pulsar. But the BMW's value is always linked with some equation. So this value always depends on this value. Whatever the input here, this will be the output. And that is what a linear regression equation is. Just that we don't have an intercept value here. Imagine we had an intercept. Let's say this value was 54. That means, what is intercept means here? Intercept 54 means the BMW value will probably start 54 kilometers after the pulsar's value. So this is the intercept. So what if we add that variable here? We can certainly do that. 54, so it will be 54 plus. That will be the only change in that equation. That's it. That will be the only change in the equation. So is it clear now? So this is the best practical example I could have think of. Similarly, between height, weight, so okay, let's come back to the basic this thing first. We understood what this is simple linear regression is. Simple linear regression. So this is linear regression. Now, why you are calling it simple? Because it has one independent variable. For scenarios where we have more than one independent variable, we will call them as multiple linear. Here we have more values, be it x1, x2, x3, x4, x5, like that. So more than one variable when we are considering to calculate the dependent variable. In that case, it is a multiple linear equation. Is it clear?
Yeah.
That is the only difference. One is linear regression, simple linear, one is multiple linear regression. So simple linear means you are considering only one variable like the Pulsar BMW example we saw. But for multiple linear, that means there will be more than one variable. That means if we are seeing this, there could be more number of Pulsar and then something, lot of other variables will be there. So that will be my multiple linear equation, and that equation will only change. That's it. So it will be 1.5 into Pulsar plus, let's say, 2.5 into some other, some other Honda, some other thing, something like that. So this is a multiple linear equation. Linear regression is same. Why linear? Because it has to be a line. At the end, it has to be a line. But either it's simple or multiple based on how many variables you are considering. So again, if we come back here, so we understood the basic simple linear and multiple linear, these things. Now let's understood these basic things. What are we doing here? So here we have one dependent, one independent, very good. We have a straight line, we have an equation. So how this straight line is coming, hitting that difference is your intercept, and how much angle is your slope. But keep it simple. How much angle is difficult and it might get confused to remember, but this is just the coefficient of x with respect to y. Right. So that is the slope of this particular x1 variable. Now, using this particular formula, we have been able to derive an equation. Let's say if I want to derive an equation, that means what I want to do. I want to draw a straight line through these points so that in future, if any other points appears, I would be able to tell you based on that line that where the next, other value will be. So one point is what? Essentially, it's 2 points, right? Like the first one, 135, 45. It's one is x-axis, one is y-axis. And same for all those points. Now, if I have a straight line that goes through these points, in that case, if I give one value of the x-axis, I should be able to predict the y-axis values as well based on that line. Where in that line that point will fall, that is something that I can predict. And that is all about linear regression is doing. First, deriving the equation, and then based on that equation, predict the future values. So let's do that. So in Python is just 2-3 lines of code, but in Excel is just simple. If I do this, yes, this is the equation. This is your equation. So what is the equation? So the equation is y is equal to 2.3333 into x. One second. Can I copy it from here? Yes, I can. Perfect. So this is my equation. Y is equal to this r square. Let's ignore r square for now. Don't get confused. So what are the values we have? Y is equal to beta naught. So here the beta naught value is negative. What is the value of beta naught? Is minus 267. So that is the value of beta naught here. Beta naught is minus 267.11. And what is the value of beta 1? The beta 1's value is 2.33. Now, if I plug in this equation here, I should be able to deduce any future values, right? So, y is equal to 2.3333 into x is equal to this into x minus 267.11, right? So now, if I give the height, it would be able to give me the weight. Okay. So that is how this works. If it falls in that line, so that is one thing that it has to take care in mind. Oh, I dropped the equation. What is happening? Right. So if I put 160, this will be my value. 100 kg. If I put 180, then this will be my value. 152, something like that. So that is how we can take the value of any future value, and we can predict their outcomes. Now the thing here is, the important thing here is, that is fine, but how to ensure if this is giving me the right results or not? That means checking if the errors are coming, or how much is the errors are we getting. For that, what we have to do here, we have to just do some more thing, which is here, more here. So this is my weight. So what weight? This is my actual weight. Here now, what are we going to do? This is my predicted weight. So what if we try to see the same weights based on this existing formula? Can we do it? Yes, we should be able to do it. So is equal to 2.3333 into this value minus 267.11. See, if I put the same formula on my already existing weights, then I should be able to judge whether, because for the new ones, I don't know if they will match or not. But for my existing ones, I know what the actual weights are. So I can probably cross check if the weights are close or off. That is something I should be able to check. So this is based on the newly equation that we have derived. Now we will see errors. Errors is equal to actual minus predicted minus 3. So this is my errors I'm getting. So for few values, we are seeing we are predicting more. For few values, we are seeing we are predicting less. And for few values, it's pretty much the same result. So once I have the errors in place, what are the things we should do? The first thing is convert them into just delete the negatives out of it. Just make them positive. So that will be known as absolute error. Absolute means just taking the absolute value. That means not positive or negative. I'm not taking all of that. I'm just taking the actual value of it. So these are my actual values. So next, what I'm going to calculate? Mean absolute error. Mean, that means this is all the error that I'm getting, but what is the average of all these errors? That is something I should also check, right? So what is the average? So the average of all the values is 3. So that is my mean absolute error. Now, so that is one thing. So understand this as one single case or one single scenario. Now, let's say there is another scenario where this line is slightly tilted. Now, I am not able to do it manually, but just imagine this line is slightly tilted like this. Probably this is the position of the line. You getting my point? Hello?
Yes, yes.
So what I'm trying to say is, just imagine there is this line, but this line is not there. Now the new line goes like this. It starts from this 60-17 between that, and it goes like this. This is the new line, probably. So if this is the new line, that means the intercept value will change, the slope will change, everything will change. Right? So in
Yeah.
that case, every single value will change. Let's try that. Let's say the new value is, let me write it down here somewhere. Let's say the new line has these values, 1.68. Randomly, I'm just making some numbers. Minus 200. Let's say this is the new slope intercept value. So if I plug in the same value here, 1.68 into 200. See, what am I going to get? This is the same thing, right? But taking a new, so this is case one. This is probably case one. This is case two. So these are individual cases. This is one case. This is one case. So here also we have done the same thing. These are the actual ones, taking the new line equation, which is now a different line which goes through this, something like this. It gives you new slope intercept values, new coefficient values. Once you plugged in, you are getting now different set of values. These are your predicted values, right? So point is the errors are also different. The absolute errors and the mean error is also different, right?
Yeah.
So you could come up with multiple such cases, hundreds and hundreds of such cases, hundreds and hundreds of such cases, because you don't know, right, if this is the right line or not. So you can just, just keep on changing the line alignment, and you would get different, coefficients and intercepts. And based on that, you come up with different results, different errors, different mean absolute error. How would you select which line is the best? One simple answer, this one, the mean absolute error. The case which has the mean absolute error as the less, you are going to select that particular variable. Right?
Oh,
That is one thing. And there is also something that you can select, which is a square root. Why? Because these numbers could be very high based on the coefficients. So to bring them under the single umbrella, mean absolute mean squared error. Oh, sorry, no, this will be here. If this is something else, yeah. Mean squared error, root mean squared error. Root mean squared error. Now, how to calculate this? I'll show you. This is the mean absolute error we have seen, which is just the average. Now, what is mean squared error? Mean squared error is, first, this is the error -3. So the squared error, what is squared error, will be just squaring this into the same one. So if I multiply this value with the same value, that will be your squared error. Or let's add this one up. This is mean squared. This is squared. So it will be easier to remember. This is your squared error. So squared error is this into this. Doesn't matter if you take this value or this value, because if you multiply it with the same value, the negative is anyway going to go out, right? So this is your squared error. Then your mean squared error is the average of all these values. 11. And then the root mean square error, that means you are taking a square root of this value. See, it's essentially the same value, 3. Same as the mean absolute error. Now try the same thing here. See, here also we are getting the same value. So this is the squared error, this is the mean squared error, and this is the root mean squared error. It's essentially same as the mean absolute error. So you can take either of the options. Either you can take this value or you can consider this as the evaluation. So if I look at these two cases, what can I observe? I can certainly say that the case one is giving me better results because the case one's error are less compared to the case two's error. So that means whatever slope intercept value we have with respect to case one, these are more accurate. These are more accurate compared to case two. Is it clear?
Yeah.
Any doubts?
Okay.
Okay, good. So that is how we select. So what we saw, we first took normal values, then we calculated the linear regression equation out of it. Once we have the equation, we tried to calculate errors. Based on multiple types of errors, we chose which particular case, which slope intercept values are better for us. So this value is certainly better. Next, what we will do, we have to test it on some unseen data. Or at this point, we can say this is our model. So our model has been built, and this is the line, and this is the more accurate line, and these are the equations. Now, what is R square? R square is basically how much accuracy you have in your model. That means how much of the variance. Now, there is a small term called variance. Variance means how the values are different from each other. How much of the values are different with respect to the straight, like how much, spread out they are with respect to the straight line. Are they following the straight line very closely, or the values are very far apart? That is known as variance, that distance. Now, R square is 0.92. That means 92% of the times the data points are connected through the straight line. For 8% times, the data points are not connected, which is not an issue. 92% is a good accuracy score. Anything more than 80, 85, 90% is actually good. So I can say with confidence that this is my model, and this is the equation. The R square value is 92, and this is the straight line. This is my simple linear regression equation. Tell me, is that clear?
Yeah.
So that is all about the simple linear regression. And the same thing, when you have multiples, it will become a multiple linear regression. Right? You understood the multiple linear regression?
Yeah.
So that is the same one, but with a twist, where instead of one variable, you will have more than one variable. That's it. That is the only tweak here with a multiple linear regression. Now, the important thing, multicollinearity problem. What is that? So we have seen correlation, how much one variable is correlated with the other variable. Now, these variables x1, x2, x3, they have a correlation with y, which is good thing. That means individually they all are connected. But if x1 is connected with x2, that means x1 is 90% correlated with x2, then that is a problem. That means in that case, if you derive a model, you are predicting the value of y, you don't know which value is affecting which variable. These individually are affecting y, but this variable is also getting influenced by this variable. So that is not the right way of doing it. And that problem is known as multicollinearity problem, where the independent variables are correlated. Ideally, the independent variables are not. Independent variables are related. Ideally, independent variables should have no correlation between them. That is it. That is the first thing you should consider. Right? So that is the thing. That is a multi-collinearity problem that we have to solve. Not solve, but yeah, there are multiple ways you can drop these variables. You can fix their coefficient values and so on and so forth. So that is how you deal with a multi-collinearity problem. Okay. Now, errors also we have seen types of errors. Which errors is, whenever the error value is less, we will consider that. Now, here we were seeing something. Okay. Now, what are the errors? So let's say this is a linear equation, right? And the red dots are the data points. The red dots are the data points. The green color things, what are they? The green color, these lines are how much the red point is deviated from the blue line. You getting my point?
Yeah.
How much differ they are? How much, distance they have? That is your error.
Okay.
So sometimes the error will be positive, sometimes error will be negative. Exactly like we were getting. Sometimes the errors will be positive, sometimes error will be negative. Sometimes the error is zero. That means probably that particular point is on the line. That
Okay.
is why the error is zero. Otherwise, the error is positive and negative. And then we will calculate a lot of things to see which the final root mean square error or the mean absolute error. And based on that, we will take a call whether we should use it or not. So that is one important thing. And there was something else here. Okay. So these could be your different lines, right? X1 and Y1. So X1 is your independent and Y is something which depends on X. So Y is your Y1 would be your dependent variable. Now, these could be your different sets of data points. Now, based on that, you have to take a call whether you need to do a linear regression or something else. There are something called non-linear regression, which are a little advanced. So let's not pay your attention towards that and don't get confused. Focus on linear regression. Linear regression means something which you can plot a graph, a straight line, and based on that straight line, you can predict the future values. So these points, the first graph, these points are pretty spread out. So the points have, that means this x1 and y1, they have a correlation, linear correlation, because it essentially takes the shape of a straight line, but the value is less. The linear correlation value will be, between 0 and 1, but probably it will be between, 6 or 7 or 0.6, 0.7, something like that. But look at this one. This is highly correlated, X3 and Y3. There is certainly one outlier, and we know if there are outliers, how to detect them and how to delete them or remove them. We know that. But other than that, all the data points are heavily correlated between them. So if I draw a line, if I know one value of X3, I can tell easily what will be the value of Y3 and put that onto the graph. This is X4, Y4 is something where we shouldn't use a linear regression because these are not numerical forecasted value. Because see, here the value is slowly increasing. But here the value of X is fixed at 8. The Y's value is changing between, 4 to 10. But X value is fixed. And 1 is at here. So this is clearly not an example of a good linear regression problem. This is also a linear regression, but here what we have to do, we should come up with a polynomial equation. A different type of, not a linear means line. Non-linear regression is something that we have to do. So these are a few of the interesting things. And once that part is done, then finally you have to do your errors. Now, how can we check errors? There are something called error distribution. So the error distribution. So what is error distribution? Error distribution. So what is error distribution? This is something like, you know, how much the errors are spread out. Let me get a good picture first. This is better. This is better. This one. So the error distribution, what that means? That means if I put that error distribution into a probability distribution graph, how much the errors will be distributed? How much the errors will be distributed? It should take the shape of a normal distribution. If the errors are taking the shape of a normal distribution, that means your model is good. Which means what? Which means that most of your errors are at zero, but there are few errors which are on the positive side. There are few errors which are on the negative side, which is absolutely normal because this is statistics. This is not real. You're predicting something. So the error should take the shape of a normal distribution. So here, if I try to see if that works or not, don't know if this will work. More or less, it's not normal, but yeah, something like that. Anyway, it's very bad, by the way. I don't know if it has this alarm bar. No, it's not coming. Anyway, so the point is the errors should be normally distributed. That is the first point. Error distribution should be normally distributed. Take the shape of a normal distribution. Take the shape of a normal distribution. And your second point has to be homoscedasticity. There has to be homoscedastic in nature. Now, what is that? That's a very small and important thing. Homoscedasticity. So what that means is, if I look at the image, this is an example of a homoscedastic. Homoscedastic means something which is distributed equally. This one, this picture, the first one. So if this is the line of zero, that means see how the errors are spreading. Most of the errors are in the zero, but the and errors are spreading on both sides, positive and negative. But the distance is same. The distance is constant, which is known as variance. This distance is known as variance. How the errors are spread out from +5 to -5. So that +5 to -5, that thing is constant. That's not changing for all the data points. That is known as homoscedasticity. Heteroscedasticity, on the other hand, is not constant. That means for few places the errors are close, for few the errors are very much spread out, and something like that. This is also an example of heteroscedasticity. So that means for these type of models, the errors are not randomly coming. So the errors are uh, probably following a pattern. That means the model has not been able to derive the equation correctly. There is something wrong with the model. So homoscedasticity. These are the two crucial points. So these are the two crucial points. If these two are satisfying for your case, that means you can say with confidence that yes, my model is good. I am getting good prediction. There are no multicollinearity. Uh, the error distributions are also pretty good. That means I can take it to production and I can use this model for general cases. Is that clear?
Yeah.
So that is all about a simple linear regression. Right? Okay. So okay, let's stop today at this time. And we have covered few interesting things. If you really want to learn, at least, remember, just go through the basics because you would be able to relate. And
Sure.
in case if you need this, let me just save it somewhere and give it to you. Oh, this is the hard prediction. This is that data. Oh, you can take that as it doesn't matter. Save as 7. 1 second. Can we not save it directly to WhatsApp?
Yeah, you can send me directly to WhatsApp also. Same
How
number.
can we do it? No, I'm saying in this Excel file.
Yeah, Excel file also we can send, no?
Okay, fine. I'll share.
Fine.
So, long story short, so this is what a linear regression is. So,
Okay.
was that interesting? So, were you able to follow what we were
Yes.
doing?
Yeah.
Now, the same thing we will do for, values where the final outcome is limited. That will be a classification problem. And for that, the techniques are more or less same, but little bit different here and there. That is a
Okay.
classification problem.
Okay. In the exact work also, we will be applying the same formula, no? Or else,
Absolutely. So what I'm doing now, I'm taking you through Excel to at least make you understand what is happening. Because if I
okay.
show you directly in Python, it will be 3-4 lines of code.
Okay.
The whole thing will be done in 4 lines. So you will not be able to understand what's happening.
Sure.
So that is why I'm going through the things in detail. So you should be able to understand what's there in the backend. But yeah, in real world, this is what you will do.
Okay.
This is what you will be doing. All right. Thank you so much. Let's connect tomorrow.